Matter waves. Einstein discovered Louis de Broglie's work and supported his ideas, which were received skeptically at first. In another major paper from this era, Einstein observed that de Broglie waves could explain the quantization rules of Bohr and Sommerfeld. This paper would inspire Schrödinger's work of 1926, 281, 282. Quantum mechanics. Einstein's objections to quantum mechanics. Newspaper headline on May 4, 1935. Einstein played a major role in developing quantum theory, beginning with his 1905 paper on the photoelectric effect. However, he became displeased with modern quantum mechanics as it had evolved after 1925, despite its acceptance by other physicists. He was skeptical that the randomness of quantum mechanics was fundamental rather than the result of determinism, stating that God is not playing at dice. 283, until the end of his life, he continued to maintain that quantum mechanics was incomplete. 284. Bohr vs. Einstein. Main article, Bohr-Einstein debates. Two men sitting, looking relaxed. A dark-haired Bohr is talking while Einstein looks skeptical. Einstein and Niels Bohr, 1925. The Bohr-Einstein debates were a series of public disputes about quantum mechanics between Einstein and Niels Bohr, who were two of its founders. Their debates are remembered because of their importance to the philosophy of science. 285, 286, 287, their debates would influence later interpretations of quantum mechanics. Einstein, Podolsky-Rosen paradox. Main article, EPR paradox. Einstein never fully accepted quantum mechanics. While he recognized that it made correct predictions, he believed a more fundamental description of nature must be possible. Over the years he presented multiple arguments to this effect, but the one he preferred most dated to a debate with Bohr in 1930. Einstein suggested a thought experiment in which two objects are allowed to interact and then moved apart a great distance from each other. The quantum mechanical description of the two objects is a mathematical entity known as a wave function. If the wave function that describes the two objects before their interaction is given, then the Schrödinger equation provides the wave function that describes them after their interaction. But because of what would later be called quantum entanglement, measuring one object would lead to an instantaneous change of the wave function describing the other object, no matter how far away it is. Moreover, the choice of which measurement to perform upon the first object would affect what wave function could result for the second object. Einstein reasoned that no influence could propagate from the first object to the second instantaneously fast. Indeed, he argued, physics depends on being able to tell one thing apart from another, and such instantaneous influences would call that into question. Because the true, physical condition of the second object could not be immediately altered by an action done to the first, Einstein concluded, the wave function co.